First well, that's loud. First we'll introduce some terminology and concepts. Because we want to download data from multiple clients or multiple other hosts. We'll refer to the data that we want to download as a torrent. Where a file that we want to download or someone wants to make available and then others to download is referred to the torrent as a torrent. And in fact, it may not be just a single file. A torrent may contain an archive of multiple files, a collection of more than one file. A .torrent file is a specific file type, and it's a meta file in that it's a file that describes the torrent, that is the file that you want to download. You want to download file A, the .torrent file describes that. In particular, describes how you can download it, some characteristics that are needed by the BitTorrent protocol. So we're going to go through how the BitTorrent protocol works in terms of the data transfer. So there are a set of computers in the network, in the peer-to-peer network, the peer-to-peer system. The users accessing a particular torrent are called peers. So in the internet, there may be multiple files available, multiple torrents available. We'll focus on the transfer of just one torrent. The users accessing a torrent are called peers. By accessing, they may be either downloading or uploading. Because how it works is that one user initially has the torrent. Some users download that torrent from them. As they download the torrent, they make it available to other users to download from. All of those users are the peers. So you may be downloading the torrent from one peer, and at the same time another peer is downloading from you. That is, you're uploading. We can classify the peers into those that have fully downloaded the entire torrent. So the entire torrent is the file that they're looking for. They are the seed. As we introduced last week, we can have clients that download a file and then make it available to others. Those clients that have downloaded the file in its entirety are called seeds. And those users are seeding the torrent. A peer that has not yet downloaded the entire file is called a downloader or a leech. They've normally downloaded something that has downloaded more than they have uploaded. So we have one client or one host which has the entire file, the torrent. So they have 100% of it. We may be having another peer which is downloading from this host. So this host is sending the file to here. This is another peer, so this is one peer. This is another peer. While it's downloading, it's a peer and it's a downloader or a leech because it doesn't yet have the full torrent. And of course there may be other peers downloading. When this peer has downloaded the entire torrent, it has 100%, it's referred to as a seed. And this one's a seed as well. It seeds the torrent for others to download from. So this peer can in fact be downloading from multiple peers. And we note that this peer is at some point is downloading before it gets to 100%. Before it's at 100%, this peer is downloading from this peer. At the same time, peer 3 is downloading from peer 2. So from peer 2's perspective, it is downloading and uploading at the same time. Peer 2 is downloading and uploading. So just be careful when we talk about upload and download, it's from the perspective of a particular peer. P2 is uploading the file to P3, or P3 is downloading the file from P2. It's the same thing. This is with respect to a single torrent. It's possible that this peer, or any peer, is downloading or is involved with another torrent as well. This is torrent 1, one file. There may be a peer with a different torrent available. Peer 2 may be downloading 2 torrents at the same time. We're going to focus just on a single torrent. It's just if you're involved with 2 torrents or 2 or more, then it's all independent. The downloading of this torrent is independent from the downloading of this one, at least from the simple perspective we look at. A swarm is the set of users or set of peers connected to a torrent. So in this simple case, the swarm for torrent 1 is P1, P2 and P3. For torrent 2, it's P2 and P4. So we're going to look at a single swarm. So the set of users connected to the torrent or accessing the torrent is called a swarm of users. All peers including the seeds. So what we want to look at is how do we do this download? How do we download from multiple peers, and how do we make it efficient? And how do we find those peers? A torrent may contain multiple files. For our examples, we'll just usually refer to as a single file. A torrent is one file, but it in fact can contain multiple files. And the torrent is divided into pieces, or files are divided into pieces. And pieces are further divided into blocks. So we have torrents, pieces, blocks. Blocks are the smallest unit. You do not have to download the entire torrent before you can upload it to others. As you download a piece of this torrent, when that piece has been downloaded by P2, P3 can download the piece from P2. So P2 doesn't have to have 100% of the torrent before others can start downloading from it. They need to download by pieces. So, and we'll see some more examples later, but if our torrent consists of 50 pieces, and each piece is 10 blocks, so there are 500 blocks, 50 pieces in the torrent, 10 blocks in the piece, then we'll see that a peer downloads blocks at a time, trying to download an entire piece. So downloading blocks. Once it has a piece, let's say piece 1, then P3 can download that piece from P2. And at the same time, P2 can download subsequent pieces from peer 1. And in fact, P3 can be downloading piece 1 from P2 and piece 2 from P1. So you can download from multiple other hosts at the same time. That becomes efficient because, or that adds, improves the efficiency because you don't have to wait for an entire torrent to be downloaded before you can start uploading it. Especially when the torrents are large files. If it's a large file, say 1 gigabyte, and it takes 2 hours to download the entire file, then if we worked on torrents only, not pieces, then we'd take 2 hours to download, and then P2 can upload to P3. But by subdividing to pieces, we can download piece by piece. As each piece becomes available, P2 can upload to P3. So P3 can download from P2 sooner by subdividing into pieces. we'll talk, or we'll see some examples of the sizes of blocks and pieces a little bit later. The set of peers associated with a torrent is a swarm. We have a special server in the peer-to-peer system, which is a tracker. That manages the list of peers in the swarm. So there's a special server, some other device, which is the tracker. Because the peers need to know who to download from, the tracker will help them with finding out who to download from. The tracker will, in the simplest form, keep track of all the peers in the swarm and some of the statistics about what those peers are doing, how much they've downloaded, and of course the addresses for those peers. So the tracker at least has an index of P1, P2, P3, that is their IP address and port numbers. So that if a new peer joins, then they can contact the tracker and find out one of the other peers to download from. We're going to focus on not how we discover other peers, but how we perform the data transfer. We saw last week with the approaches of the Nutella, the fully distributed, the Napster, the centralized approach, and the in-between, the fast-track approach of how to find other peers. Given a resource, how do you find a peer that offers that resource? We'll see after BitTorrent another approach, a fourth approach called distributed hash tables. In theory, all of them could be applied with BitTorrent. In practice, BitTorrent initially used a centralized based approach, use a server, but in fact in most cases today it uses the more advanced approach, which we haven't gone through yet, distributed hash tables, a more decentralized approach. But we're going to focus just on the data transfer aspect. There's another server, an indexer. It manages a list of torrents. It's typically just a web server, which keeps a track or a list of .torrent files. .torrent files are files that describe a torrent. An indexer keeps a list of those .torrent files, or it keeps a set of those .torrent files. We'll see that these .torrent files contain the address of the tracker. So for a peer to join the peer-to-peer system, we have an indexer which has a list of files including torrent1.torrent, a file that describes the torrent used exchanged in this peer-to-peer swarm. This file includes the address of the tracker, so a new peer goes to an indexer, obtains this file, the .torrent file, which includes the address of the tracker, so they go to the tracker, and the tracker contains a list of the peers, P1, P2, P3. P5 goes to the tracker and says, I want to learn about some peers in this swarm. The tracker returns a response, tells them some of those peers, and then P5 can start downloading from those peers. That's an example of how we divide the torrent into pieces and blocks. A torrent is, in fact, can be a collection of files. So it may be just one file. In this example, there are 3 files of different sizes. So we combine those 3 files together in the example. That's our torrent. That torrent is divided into pieces, equal size pieces, usually of some predefined size. Equal size except for the last piece, just so that the last piece can be smaller than the previous pieces. And then pieces are divided into blocks, again of fixed sizes. I think we'll see later that a typical size may be 16 kilobytes for a block, 256 kilobytes or 512 kilobytes for a piece. And a torrent can be any size. Depends upon the files that have been made available. We download blocks one at a time, normally trying to download all the blocks in a piece. So if we want to download piece 1, we'd download block A, B, C, D, all the blocks in that piece. Once that piece is fully downloaded, we can make it available for other peers to download. And any questions? Almost finished the semester. Last topic. Any questions so far? If you have, just raise your hand. Don't ask others. We'll see the data transfer protocol operates on blocks. We exchange blocks at a time, but normally we aim to download all blocks of one piece, but the pieces that we download from the torrent do not have to be in order. We do not necessarily download piece 1, then 2, then 3, and then n. The way that we select the pieces to download can be quite important. We'll see that later. So let's go through the steps of what a peer does. So what is a peer? It's a piece of software running on a computer which has an IP address for the computer, a port number. So we normally identify the peer by its IP address and port number. In practice, sometimes the application can have a unique identifier as well. So the port number, the IP address, and some application ID is used to identify that peer in the swarm. So this is a new peer. Initially, it doesn't know of any other peers. So it's turned on a computer in the internet. It wants to download some file. It needs to go to an indexer, a special server, normally just a web server, that keeps a list of .torrent files. And it obtains the .torrent file it's interested in, based upon the file name. The indexer has a list of known torrents, maybe not all torrents available, but a selection. The process of obtaining this .torrent file is not part of the BitTorrent protocol. So BitTorrent is in fact a protocol. It's a specific protocol. It's also an application, and it's also used to refer to an entire network. But there's a protocol called BitTorrent for data transfer. It doesn't include how to get the .torrent file. Normally you just use HTTP. That is, the indexer is a web server. It has a .torrent file on the web server. You open your web browser and go to that indexer and download the .torrent file. And then that .torrent file is normally used by a BitTorrent application that implements the BitTorrent protocol, the client software. So the next step, after you find the .torrent file from the indexer, the .torrent file describes the files contained in the torrent and gives some information about the tracker. So it gives the address and the port number of the tracker server. It tells this new peer, P5, that's just joining the swarm, who the tracker is. More than one trackers can be listed, so that we can have multiple trackers for a particular swarm, but at least the address, the IP address and port of this tracker, so that the new peer can contact that tracker. That's contained in the .torrent file. We'll see an example shortly. So the peer then contacts the tracker to obtain a list of peers in the swarm, because that's what the tracker does, keeps track of the peers in the swarm. Yep?
But sometimes I found out that the tracker also lists the peers that isn't in the swarm. It's like they're active, but they're not.
Normally, so in the swarm, all the peers associated with that torrent, but how do we know that they're associated with that torrent? How do we know that P3 is downloading from P1 and P2? So in the past, P3 contacted the tracker. Tracker added P3 to the list. How do we know that P3 is still downloading from P1 and P2? That is, how does the tracker know that P3 is still in the swarm? Well, there needs to be some regular updates. It could be that P3 has turned off. It's a computer, it's turned off. The tracker doesn't know that unless there's some update. So there's some update interval normally where the peers contact the tracker. So the information that the tracker has may be out of date. If the peers only contact the tracker every 30 minutes, then if the peer leaves, then the tracker's list of peers may be out of date. So that may be one thing that you see, that the list of peers from the tracker is not perfect because it needs to be updated over time. Peers can join and leave the network as they wish. Yeah?
In some BitTorrent website that they implement the ratio system, how does the node, the amount of data?
So we'll see shortly that for the system, for the BitTorrent network to be efficient, then peers that upload, peers that download normally need to upload the same amount of data. So that because we need, if we want to download from multiple peers, we need to make sure that those peers have the file available. And to encourage that, you'd like every peer to upload as much as it downloads. Some ratio between upload and download becomes important. How do we enforce that? The BitTorrent protocol, while you're transferring data, tries to enforce that by, when we download a piece, making sure that you upload a piece at the same time. We'll see that in the transfer when we go through the details of how do we actually exchange the data. So we'll come back to what are the approaches for making sure that ratio is reasonable. We'll get to that in a moment. What we've done is we've contacted the tracker. Tracker gives us a list of peers. The tracker maintains a list of peers in the system, in the network. It may not be up to date. It's a peer-to-peer system. Nodes join and leave at different times. It's difficult for a central node to keep track of what all those peers are doing. So normally they update on a regular basis. At the time that P5 contacts the tracker, the set of peers known by the tracker may not be exactly the same as the set of peers in the system, but it should be similar, or at least contain some of them. The tracker tells the new peer a list of peers in the swarm, not all of them, but a subset. And from that, this new peer knows about other peers in the swarm. P5 knows about P1, P2, and P3. Of course, there may be other peers. In this example on the screen, there are just 5 peers shown, but imagine that there are 5,000 peers there. The new peer knows about a subset of them. And then that new peer contacts other peers in the swarm and begins the process of downloading, because the objective of this peer is to download the torrent and preferably also make it available for others to download, to seed that torrent. So we need to how do we download that torrent, which comes back to one of the previous questions. The peer maintains some contact with the tracker, so some regular updates about what it's doing. It provides statistics about how much it's downloaded and uploaded, its current status. And the peer may also get addresses of new peers from the tracker, because as new peers join, the tracker keeps a list of those peers. This peer wants to know about other peers in the network so it can download from them as well. It may get an updated list from the tracker. on a regular basis, maybe every 5 minutes, every 30 minutes, depending upon the configuration. The more often, the more accurate, but the more overhead of communications. That's the basic approach. Let's look into some details of how the data transfer works and what the format of the files are. We said the .torrent file is a meta file. It's a file that describes the torrent. The torrent, remember, is one or more files that we want to download. We want to publish and make available for others to download. The .torrent file describes that. It contains different fields in this file. It's just a text file, but contains fields with values. They encoded in some format, not encrypted, but just given some specific syntax that a computer can read easily. Some of the fields, there's an info field. This describes the files in the torrent. If you go back, just remember, a torrent may have multiple files. A torrent can be broken into pieces, which are then broken into blocks. The .torrent file describes those multiple files in the info field. It includes the file names, so the name of the files inside, their length, the length of pieces, and for each piece in the torrent, a hash of that piece. We've mentioned hashes before, but a hash algorithm takes some value and returns a practically unique fixed size hash value. So we have our torrent. You have this slide. I'll redraw it. Divide it into pieces. Piece 1, piece 2. In my example, 5 pieces. We apply a hash algorithm. The hash algorithm we use is called SHA-1. It's just an algorithm that takes as some input the data, in this case the bits in piece 1, not the name of the file but the actual bits, and produces a hash value, a short, in this case 160-bit value, which should be unique. That is, if you take the hash of another piece, which is a different sequence of bits, you'll get a different hash value. H1, H2, H3. With a 160-bit hash value, you have 2 to the power of 160 different possible values. So, therefore, there's a high chance that it will be unique. The chance that 2 different values produce the same hash value is very, very, very small. Practically impossible. So the hash values of the pieces are stored in the info field in the torrent file. The other thing in the torrent file, the .torrent file, is the announce field. That's some address of the tracker. Remember, what the new peer does is obtains the .torrent file. Inside that file, it tells the new peer where the tracker is. And that is told in the announce field. It's a URL. So a domain name, an address for that tracker. And it may be more than one tracker. It may be a set of trackers, a list of trackers. The date when the torrent was created, some name of the software that created it, and some textual description of that torrent can be included. So that's the .torrent file. Here's an example. We say a text file with various encoded fields. So there are these fields, but they have some particular syntax, which we'll see here. The syntax, we're not going to try and explain. It tells something about what the content of that field is, whether it's an integer, a date, a string, and the length of that field. That's what this D8, 7, 13, and 4 do. They indicate 8 is the length of the field name, announce, 7 is the length of this field name, 13 is creation date, 4 is info, that's the length of the field names, and then the length of the actual field value. So here's the value. But the basic way that we interpret this, a field name, a field value. Announce contains the address of the tracker, so it's a URL. And inside that URL, it specifies the access protocol, the domain, the port number. So even though we're using HTTP, it doesn't mean the tracker needs to use port 80. So if this tracker is, our example, has the domain name torrent.ubuntu.com, and that has an associated IP address, and the port number it's using or listening on as the tracker is given in the URL, 6969, 6966. So that identifies this computer on the internet and the application. The next, okay, then we have a comment that just describes the contents of this torrent. Some date, it's given in a format that can be converted to a universal time date. And the info field, which contains the length of the torrent, the length of this. In this example, it's 732 megabytes, so the length in bytes there. The name of the file, in this example there's just one file. In general there may be multiple files in here, but in this example just one. And then the length of each piece, 524 kilobytes approximately. So that's in bytes. So each piece in the example is about 524 kilobytes. And then the number of pieces. In this case, 27,000, almost 28,000 pieces. Because if each piece is half a megabyte, is that right? We have 730 megabytes. You can do the calculations if that's half. Does that add up? Does that add up? 27,000 times 524,000, what's it equal? We've got someone with a calculator, a glorified calculator. What's 27,960 times 524,288? 27960 times 524,288 times, his calculator doesn't have times. Multiply it. Multiply by, his calculator's crashed, has it? Multiply by 524,288 equals 14 billion. Why? What's wrong here? I have to check what this value is. I'm not sure. It doesn't look right in terms of the number of pieces. What's this strange thing? So it says here I calculated 27,000. I think it's the number of pieces, but the number doesn't look correct, but we'll check that later. This is the hash of the piece. The info field includes the file names, the file length, the length of the pieces, 524 kilobytes, and for each piece, the hash of that piece. And all right, when I show it in a text editor, it comes out as some strange characters, but it's just some binary value, 160-bit value for each piece, because the hash we're using is SHA-1, which produces 160-bit output. So 160 bits for piece 1, 160 bits for piece 2, and for all the other pieces. That's an example .torrent file. When our new peer obtains that .torrent file, it knows the tracker to contact from the announce field. The tracker is acting as a web server, so it implements a HTTP server. The peers communicate with the tracker using HTTP, but not in the normal way that we think it's used. We normally use it as you send a request for a file, the server sends back a file. We're using it slightly differently, in a valid way, but different than what we normally use it for. So the peer, when it wants to join the network, sends a request to our tracker, and the tracker sends back a response. They actually use the HTTP request and response to exchange information, not just for the peer to learn information about other peers. When P5 joins the network, it needs to know a list of other peers, sends a request to the tracker, tracker sends back a response containing that list of peers. That's one thing. But also later, while the peer is in the network, in the swarm, the peer will send updates to the tracker about its statistics, also using HTTP. So how does a peer send data to the tracker? It sends it in the GET request, in the URL. So a peer sends a HTTP GET request. The URL in that request contains some useful information. Let's make this a bit clearer. Make some space. Our tracker has a list of peers. We send a request. We know the format of a HTTP GET request, GET followed by some path or URL /index.html, but it can be more complex than that, followed by the protocol and some options. There are many options available. That's the request sent from the peer to the tracker. What does it contain? The URL contains information about the peer activities. So the identity of the peer, the port number used by the peer. So this uses a port number for others to contact via. So that's told to the tracker. The amount of bytes uploaded and downloaded so far. So if this peer has downloaded nothing so far, the value will be 0. But once it starts downloading data and it sends an update to the tracker, it will say how much it's downloaded and how much it's uploaded of that torrent. And that's sent in this GET request. The status of the download, whether they've started the download, whether they've stopped, finished, or stopped, that is like paused the download, or completed, that is they've become a seed. And there's some other statistics it can send as well. That is sent from the peer to the tracker. The tracker sends back a normal HTTP response. It contains plain text and it contains some information that the peer needs. A list of peers, that is a list of other peers, their identity, IP address and port number, in the same way that this peer sent its identity and port number, and of course when the tracker receives it, it knows its IP address. The tracker maintains a list of those for each peer and sends a subset of those peers back in the response, so that the receiving peer learns about other peers. Some statistics about the number of peers in the swarm, the number of seeds, that is peers that have completed the download and incompleted. So if we have a swarm of 10,000 users, there may be 1,000 seeds and 9,000 leeches. The tracker keeps track of that. How does it know? Because the peers send their status update. It knows which peers have started, stopped and completed. Those that are completed are seeds. The client or peer needs to regularly send updates to the tracker. At what interval? The tracker tells it. That is, the tracker tells this peer in the response, send me an update every 30 minutes. 30 minutes later, the peer will send another HTTP GET request with its statistics, and the tracker will send back a response. And if there is any problems, then there are other fields that can be included in the response, errors and warnings. So they just keep doing that according to the update interval that the tracker chooses. Recall, we're just focusing on one torrent, one swarm. There's nothing stopping these peers for doing the same with another swarm to another tracker, but it's all independent. This illustrates with a little bit more detail. This is the GET request going from peer to tracker, the blue one, and the red one is the tracker responding, the HTTP response. See, the GET request has a long URL. Get/announce, because that's what the tracker, that's what the .torrent file gave as the URL for the tracker. And then we encode in the URL some parameters. And the typical, the way to do that in a URL is using the question mark, parameter name or field name equals value. And then ampersand, parameter name equals the value. I've introduced spacing in here just to make it a little bit clearer on this slide. In practice, there's no spacing. It's just one long string, one long URL. And that's the format in any URL. Question mark, parameter name equals value, ampersand, and then so on for each subsequent parameter. So we see some of those parameters from the previous slide. The peer ID, this is sent from the peer to the tracker, the peer's ID, the port number the peer is using, the amount that it's uploaded and downloaded. So when it first contacts the tracker, it's uploaded and downloaded nothing. It's just joining the swarm. How much it's got remaining of the total, it's got 730 megabytes remaining. If there's any corrupted pieces that it's received, what status, whether it's started, it's stopped or completed. The address, the IP address. Then the rest, the last three lines are just normal HTTP options. So the information sent to the tracker is encoded in the URL. The tracker sends back a response as a normal HTTP response, HTTP 200 OK, and included in the response is just plain text, which includes fields and values. The number of completed peers in the swarm, the number of incompleted peers in the swarm. Let's see if we can interpret that. Complete, I means the value is an integer, 1328. And then the next field, incomplete, integer 97. So there are 1,328 seeds and 97 leeches in this example. The interval for which the peer needs to recontact the tracker, 1,800 seconds, every 30 minutes in this case. And the other statistics, as we listed here, the list of peers. So it's not shown here, but information that indicates, gives a list of peers, their ID, their IP address, and their port number. And that continues every 30 minutes in this example. And in practice, the peer may be doing that to multiple trackers, not just one tracker. Now, let's look at how the data is exchanged. Once our peer knows about other peers, he wants to download the file, the torrent. How does it do that? What's the peer exchange protocol? So between peers, no longer with the tracker, we exchange data. That is, One peer is downloading data and also uploading to other peers. So we've got an exchange protocol, a peer exchange protocol. What we do is we create a TCP connection from one peer, let's call it the client, to some remote peer. So from the perspective of our peer, the client, we connect to some other peer, some remote peer. And we exchange messages to inform about the current status and downloaded blocks. So there's some initial startup phase. Let's look from the perspective of this peer, let's call it the client peer. It's going to contact at least one other peer, let's call it the remote peer. And it exchanges messages, so it creates a TCP connection, SYN-ACK, creates a connection, not using HTTP, using the peer exchange protocol to send messages. And there are different message types, we'll see some of them here. So we establish a connection and send messages in both directions. So you're experienced programmers, you could implement such a protocol using sockets. You just create a client and server socket, and the data that you send across that connection using sockets would be the format specified by the peer exchange protocol. So some of the messages sent, there's a handshake message at the start. So as soon as the client peer contacts the remote peer, the client sends a handshake message. It lets the remote peer know of its ID. It just tells the remote peer who it is, the peer ID. It may be, and as often is, followed by another type of message called a bit field message. The remote peer tells the client the set of pieces it has available to download. So in our example, let's say the torrent consists of 100 different pieces. This remote peer has already downloaded some of those pieces, maybe all of them, maybe just a selection. Let's say it has different pieces. P here is a piece, not a peer. So it may have a list of pieces that it's already downloaded. The bit field message encodes that set of pieces. So it says, I have piece 1, 3, 72 and 99. That's what the remote peer tells the client peer. So now the client peer knows that the set of pieces that the remote peer has available. Once we've done the handshake, and optionally the bit field, we don't have to do the bit field, then either peer, either client or remote, can start to request pieces and request specific blocks in pieces. So the data exchange can go in both directions now. Different types of messages. A request message sends a request for a specific block. So we exchange blocks with the intent of getting all the blocks in a piece and eventually getting all the pieces in the torrent. Once we've got all pieces, we've downloaded the entire torrent. We're a seed. But we exchange blocks using the peer exchange protocol. So our 4 pieces that we have here may be subdivided into blocks. Block, let's call this block 1A, maybe block 1B. That is this one piece. Piece 1 is divided into 4 blocks, A, B, C and D. And similar, piece 3, let's call them block 3A, block 3B, block 3C and block 3D. And similar for the other pieces. Now they don't have to be named like this, I'm just giving those names so I can refer to them in the example. So a peer requests a specific block. Our client peer, for example, has no pieces. It knows the remote peer has 4 pieces, because if we sent the initial handshake, and then if the remote peer sent the bit field message, the client peer knows the pieces that the remote peer has. It wants to download them, so it sends a request for one of them. How does it choose which one? We'll come to later, but let's say it chooses, okay, I want to first download piece 1, and the first block in that is block 1A, so it will send a request message for that specific block. I request block 1A. Please send me block 1A, that's what it means. And the response, if everything's okay, is that the remote peer responds with the block 1A. And the name of that is confusingly called a piece message. Why is it confusing? The name of the message is called a piece message, but the contents is a block. It's not an entire piece. This is a request for some block. This is the block coming back. For some reason they named it the piece message, but it's in fact, a better name would be the block message. And that's it. We've exchanged or we've downloaded a piece of data. Then we can send another request for another block, normally the next block in the same piece. We'd usually try to get the entire piece before we move on to another piece. So request B1B, B1C, B1D. Once we've received all those blocks, we have piece 1 at the client peer. So there's some other types of messages. We can, if we request a block, we can cancel that request if we no longer need it, because we may be downloading from multiple peers at the same time. The client peer may have another connection as well with another remote peer. So although we showed it for one, you may connect to multiple peers. And that may have pieces as well. And in fact, more than 2 peers. So this client can be sending requests to multiple peers at the same time. So remember, the peers are just computers on the internet. It has TCP connections to each of them and can send requests to different destinations based on its choosing. And it's possible that we could send a request to 2 remote peers at the same time. We get the response back from one, therefore cancel the request to the other. We no longer need it. So we can cancel. Keep alive. When we open a TCP connection and we don't send anything across that connection, then that connection will eventually close. That is, TCP software on your computer will automatically close the connection after, say, 2 minutes. If you don't use it, it will close. Keep alive is just to make sure that if nothing has been sent over some time, we send a keep alive message just to keep it open. Because if it closes automatically, then we'll have to open it again later. So sometimes we'll try and keep the TCP connection open for a long time. Minutes, hours possibly. Even if nothing's been sent, it can be efficient to keep it open just in case we need to send something shortly later. And the other is a have message, which a peer sends to the other peer saying, these are the pieces I have. So we do that at the start using the bit field message. At the start of the connection, we can advertise which pieces we have, but during the data transfer, we can also indicate what we have. Because this peer, this remote peer, is also downloading from other peers. So it's building up its set of pieces. So sometime later, if this client peer wants to know about what it has, so it can send a have message saying, these are the pieces I have now, because the set of pieces changes over time. it increases. So they are the types of messages in the peer exchange protocol, and the main ones for getting the data, we request a block and we receive a block in the piece message. And it can happen in both directions. In my example, I was just sending a request to the remote peer, but the remote peer can send a request to the client peer, because the client peer may obtain blocks from pieces from elsewhere, and therefore if the remote peer doesn't have the piece that the client does, it may send a request for that piece and download it. Getting close to one of the questions about how do we make sure that we have a ratio of upload and download. Well, for our peer-to-peer file sharing to work, we knew that the concept is if we have a single server and everyone downloads from that single server, is not as good as having a single server that a few download from and then everyone downloads from those few, those seeds. That it's more efficient if once you've downloaded the file, others can download from you. That's the concept here. But how do we make sure that a computer or a peer allows others to download from it? Sometimes peers just want the file. This client peer wants to download the file. It always sends requests, downloads pieces, but doesn't respond if peers send a request to it. That's a problem. That is, if this one does not allow others to download from it, and then everyone does that, then our system will not work. We want to make all peers such that they can both download and upload the file. There are different ways to encourage that in the system, and one way is the BitTorrent implements an algorithm called a tit-for-tat algorithm that says that if you download a piece or a block, you should upload a piece and a block. For every piece downloaded, upload a piece, with the aim of maintaining an equal amount of upload and download. That's the idea of the protocol. So the client follows some algorithm. Every time it sends a request and receives blocks, once it's downloaded a piece, it should respond to enough requests such that it uploads a piece to someone else, or someone else downloads from it. And that's implemented inside the protocol, that algorithm, such that on average that the number of downloaded and uploaded pieces will be the same. Of course, that only works while a peer is connected to the swarm. So while this client peer is trying to download pieces, while it's still a leecher and not a seed, this algorithm of maintaining equal upload and download should work, and generally does. That is, this client, in order to download a piece, it must upload a piece. And the algorithm is that if you download pieces and you do not upload, then the other peers will not download or not send to you anymore. So if the client downloads 10 pieces from the remote peer but does not respond and send any pieces back to the remote peer will start blocking the client peer. It will not respond to the client peer. So there's a way for a remote peer to not respond to requests, to slow down the client peer from downloading. If the client peer downloads everything, all the pieces in the torrent, and then the client peer disconnects from the internet, of course we cannot force it to keep uploading. But once it's associated with the network, once it's in the swarm, and if it wants to download, while it's a leecher, we can force it to keep uploading. Once it becomes a seed, we cannot. So how do you maintain a ratio or force it to have a ratio then you need some external mechanisms to force that. Note that the client peer continually sends an update to the tracker about how much it's uploaded and downloaded. So the tracker keeps some statistics of how much this peer is uploaded and downloaded. So potentially what could happen if this peer has downloaded 5 times more than it's uploaded, the tracker may no longer respond to it, saying you have not uploaded enough, therefore I will not respond to you and I will not tell you about any other peers. Similarly, other peers can block this peer if they think it hasn't contributed enough to the upload rate. How does it do that? Well, there are 2 concepts used, choking and being interested. What does choking mean? What does choking mean? Grab by your neck and do what? Yeah, and more generally means to choke is to squeeze, to, I guess if you're talking to a person, to remove the flow of air into their lungs. Well, here it's to slow down, to remove the flow of packets. So when we say we want to choke something in the network, we slow it down. So in the BitTorrent peer exchange protocol, when a client is choked by a remote peer, that means that no requests will be handled by that remote peer. Let's try and draw that. Of our client peer and remote peer. Now our problem is that if we want every peer to upload as much as they download. What a peer wants to do is download, okay? But for the system to work, we need it to be also upload. Because if it just downloads, then we're no better than just using a normal server. So what we need is that the peer both downloads the pieces it wants, but also uploads those pieces to others, so that we share the load amongst all of them. So these 2 mechanisms that we use, or 2 variables we use, are whether a peer is being choked or whether a peer is interested. Choked means that if actually, there are 4 variables maintained by a peer. So let's say 4 variables are am choking, that is I am choking, am interested, peer choking, and peer interested. Let's look at the choking first. Think of them as Boolean values. They're all either on or off, true or false. And they're for a specific peer. Let's call this remote peer 1. For remote peer 1, client peer maintains these 4 variables. What do they mean? Am choking means that the client is choking the remote peer. If this is true, that is, the value of this variable is true from the client peer's perspective, it means currently this client peer will not respond to requests. That is, the client is choking, the client, I am choking this remote peer. If the remote peer sends a request for a piece, it will not send back the piece. Why would it do that? If, for example, the remote peer has sent many requests for pieces in the past, maybe requested and downloaded many pieces, but the remote peer has not responded or has no pieces for the client peer to access, then from the client peer's perspective, the remote peer is not uploading anything of value to the client and therefore may stop it from downloading from the client. So if the remote is not sending any pieces to the client peer, eventually the client peer may decide to choke the remote peer. Stop the remote peer downloading from the client. Set the M choking value to true. Similar, it may happen in the opposite direction, that the remote peer chokes the client peer. If the client peer has been downloading a lot from the remote peer may say, no, okay, that's enough, I'm not going to send any more pieces to you, and the remote peer may choke the client peer. And if that's the case, the peer choking value will be true. That is, from the client's perspective, the remote peer is choking me, is slowing me down, or stopping me from sending. So that's the meaning of those two variables. And then the interested variables are whether we have pieces which are of interest to each other. So if one peer has pieces that the other one does not have, then that other peer will be interested in those pieces. For example, client peer has pieces P1, P3, P7. Remote peer has P2, P4, P5. So they have some pieces. Then most likely the client peer is interested in the pieces of the remote peer. I am interested in the remote peer's pieces because they are pieces that the client peer doesn't have. Client only has 1, 3 and 7. Remote has 2, 4 and 5. It would like to download 2, 4 and 5. Similar, the remote peer is interested in the client peer's pieces, and therefore peer interested is probably set to true. If they are true, and these two choking values are false, then they'll exchange pieces. They'll accept each other's requests. That is, the client will send a request to the remote peer. The remote peer is not choking our client. The remote will send back a response, send back a block of a piece. Similar, the remote peer can send a request to the client peer, and the client will respond. That's the ideal case. They're both interested in the pieces each other have, and they're not slowing each other down. They're not choking the others. What about another scenario? Client peer has pieces P1, P3, P7. Remote peer has pieces P1 and P3. What is the value of M interested? True or false? From client peer's perspective, what is the value of M interested? Is the client peer interested in the pieces of the remote peer? Hands up for true. You've got two options, true or false. Hands up for true. Anyone? Hands up for false. Hands up for no idea. In this example, the remote peer has 3 pieces of the torrent. We want to obtain all pieces. The client has the remote has 2 pieces, 1 and 3. The client has 3 pieces, 1, 3 and 7. Is the client peer interested, from the client peer's perspective, am I interested in the pieces offered by the remote peer? No, it's false. Because I already have those pieces. I already have piece 1 and 3. There's no need for me to download those pieces. So the client peer is not interested in the remote peer's pieces in this example. Is the remote peer interested in the client peer's pieces? Yes. Piece 7, it's at least interested in. The remote peer would like to get piece 7. Are they choking each other again? That's separate. If on the past they may have started choking if the remote peer maybe had not downloaded, we could be choking that. So the 4 different variables maintained, the values of them indicate whether you can send a request or not. If the remote peer is choking the client cannot send a request. Similar in the other direction. If the client is choking the remote cannot send a request. Will they send a request? Only if they're interested. And you'll only be interested if the other has pieces that you don't. So those variables change over time. They're not fixed. They depend upon the pieces available and what's happened in the past in terms of responding to those pieces. And other factors as well. It's more complex as to when do you choke someone, because if they send you pieces but very slowly, that may be another reason not to transfer pieces from them. So you may choke that other peer if they're not delivering data to you fast enough. And with a combination of those variables and the algorithm to set those variables, the intention in the BitTorrent protocol is that all clients will, it's in their interests to upload as much as they download. Because if everyone does that, then everyone will be able to transfer the data. Any questions before we move on? So you look at the past exams and then a question, for example, a question, what are the values, or given the 4 values of these variables, what's going to happen next? Given the current status of the client is this, can the remote peer send a request to the client peer? Can the remote peer send a request to the client peer? Ignore this, just look at the 4 variables. Yes, can the remote peer send a request to the client peer? Yes, it can send a request because the client peer is not choking the remote peer. Then, will it send a request? The remote peer is interested? Well, yes. It's interested in a piece, it can send a request. If it was not interested in a piece, then it will not send a request, even if it can. So, depending upon the values of those variables, different situations can arise. And the values are set based upon the pieces available and the past exchanges. And how do we tell the other node about whether we know that the peer is choking me? There are some messages to do that. Choked, unchoked, interested, uninterested. The client sends a choked message to the remote peer. The remote peer now knows it's choked. So peer, I am choking. If that becomes true, we send a choked message saying we're choking this peer, and this peer now updates its 4 variables so that peer choking becomes true. Okay? Every peer has their own set of 4 variables for every connection. If the client peer connects to another remote peer, it has another 4 variable values, independent. And we tell the other peer of what's happening, the current status, using these 4 messages. And the peer implements a choking algorithm to determine when to choke and unchoke peers based upon those past experiences. So including how many pieces the remote peer has sent to you and at what speed, for example. So the choking algorithm can be quite complex. We've looked at just a single connection. In practice, a single peer has connections in parallel to many other peers. You may have connections with tens of peers. It may vary, 10, 100, but tens of peers. Generally, only several of those are unchoked at any one time. That is, my peer is connected to 100 other peers, have TCP connections. I choke 90 of them and only unchoke 10 of them. And we can transfer the data over those 10. As the status changes, I may unchoke some of those 90 and choke some of the 10. Normally, the number unchoked will be reasonably small, but the number that we connect to in total will be larger. Why do we change? Because those other peers may get pieces that we're interested in. If another peer that we've choked, after time, it gets some pieces that we really want, that is, we need and no one else has, then we may unchoke them and start downloading from them and exchange pieces. That tries to summarize some of those concepts. Okay, we have a swarm, many peers in the swarm. From the perspective of this one peer, it has connections to a selection of those peers in the swarm, maybe tens of connections, 100 connections. Of those connections, a small subset are unchoked, the blue ones, and the rest would be choked. That is, we are not responding to those other peers. But if another peer, so currently this one is choked, this one is not, but if this one starts to get some pieces because it downloads from other peers, some pieces that our peer wants, then we may unchoke that connection. And possibly choke a connection here if this peer was downloading or sending us data slowly, or had no longer any pieces available for us that we're interested in. So it changes over time as to who we choke and who we don't. You had a question before. Has it been answered yet? What was the answer?
I asked about the ratio.
So you asked about the ratio. How do we maintain the ratio? So the ratio of upload and download is the exam question. How do you maintain the upload and download ratio in BitTorrent? The BitTorrent algorithm, there's two parts to it. The BitTorrent algorithm maintains the ratio, or the choking algorithm maintains the ratio by choking those that are not uploading enough, such that they won't be able to download anything. So if a node is not, or a peer is not uploading anything, it will eventually be choked and therefore will not be able to download anything. If it wants to download something, it will need to upload something. So that's the approach there. So over time, on average, that maintains an equal upload-download ratio. But once a peer has downloaded every piece, it becomes a seed. Okay? It's downloaded all pieces. It's no longer interested in any pieces. It can no longer download any pieces. It has no need to download. The only purpose would be to upload pieces. There's nothing to stop that peer now from not uploading pieces, because there's no motivation for it. From the protocol's perspective, that peer has downloaded everything. If it stops uploading, we cannot we cannot force it to upload anything. There's no motivation to upload anything. So once a peer has downloaded everything, normally it's difficult to force it to keep uploading. If the peer is a good peer, it will keep uploading, even after it has downloaded everything. Now, when we say that we got an equal upload-download ratio, it's not perfect. That is, over time, over a long period of time, it may be equal if those peers stay attached to the swarm. But if they leave the swarm, then it may not be 50-50 ratio. So the protocol has a way to try to aim to that 50-50 while they're attached to the swarm, but it's not perfect in that a node can leave the swarm at any time. Almost finished. We said that a torrent is broken into pieces, which is then broken into blocks. How big are they? There are no fixed limits, but typically, no fixed limits of the torrent, but we typically talk about megabytes to gigabytes. If it's too small, then there's not much efficiency gain of using BitTorrent from transferring the data. It may be just as fast to download it immediately from a server. So normally large files are used. How big are the pieces? Normally they are fixed at, say, a value like 256, 512 kilobytes, a megabyte, maybe larger, but they're usually defined. And the blocks normally around 16 kilobytes. We had an example where our remote peers had a set of pieces. Some may be overlapping. Which one do we download first? Do we download piece 1? Do we download piece 100? Which peer do we download first? Different approaches. Random. Just randomly choose a piece. That works. Another more common option, though, and better, is rarest first. Let's expand our example here. We have another remote peer. Let's look from the client's perspective. Which piece is the client peer going to download first if we use the rarest first algorithm? Which piece? Remote peer 1 has piece 137299. 2 has 3272. Remote peer 3 has 231099. The two pieces which are the most rare are 1 and 10. They only occur once. Okay, in this very simple example, the other pieces, there are multiple copies of them. So download the one that is the most rare in the network, with the idea that, okay, let's get it now just in case this peer disappears. If this peer leaves the network, piece 1 is no longer available from anyone. That would be bad. So download the piece which is least frequently occurs in the set of pieces. Yep.
I've noticed that sometimes choose to download the piece which has the data from two files that overlap in one piece. I don't know what's the reason. It choose that first to download the pieces.
Again,
it's like many times I've noticed that my client program choose to download the piece which has data from two separate files.
It downloads a piece from one file and then from another file.
Yes, it's a piece that has information from two files.
Overlapping. I don't know why it would do that. I know there are more complex algorithms. That is, you can give priority to different files. So give priority to the files. So a torrent is made up of multiple files. You can say give priority to the pieces belonging to a particular file. But why would it get an overlapping piece? I don't know. I don't know enough about the detailed client software. Some clients may implement slightly different algorithms. I'd have to check that. But the user can give some priority. That's one thing. What else could happen? Unless it's because it's the rarest piece, I don't know. Yeah. It may depend upon what the other peers have on offer, or it does depend on what the other peers have on offer. The last concept we'll introduce is availability, which measures the number of copies of a torrent in a swarm. Because there are many peers, there may be seeds. Some of those peers are seeds. Some have different sets of pieces. The availability of one means that all pieces are available at the peers in the swarm. That is, if our torrent was made up of 100 pieces, piece 1 up to piece 100, if all of those 100 pieces were available right now, and just one copy of each of them, then the availability would be 1. If there were 20 copies of every piece available in the swarm, that is, piece 1, there are 20 copies distributed, piece 2, another 20 copies of that, then we'd say the availability would be 20. If there are 20 copies of the entire torrent available, then the system availability is 20. If there's less than 1 availability, it means not all pieces are currently available. There's no way to download the entire file. If the availability is less than 1, then that means that, for example, if it's 0.5, it means only 50 of the 100 pieces are currently available. The other 50 are not available from the peers connected to the swarm. You'll have to wait some time before you can download the rest of the pieces. That is, wait for other peers to arrive that offer those pieces. So that's one way to measure how much or what's the likelihood that you can download the file, and also the speed at which you can download the file. Because remember, in general, the more peers that have the file and have the pieces, the faster you can download. Higher the availability, the faster you can download. There are many other issues and many more details of the algorithms we will not cover. Some issues that affect performance, how many peers to connect to. A client, how many remote peers to connect to at once is normally in the order of tens of peers, 10, 30, maybe up to 100. What's the optimal number of peers to download from an unchoked peer? What should the best size of the piece and block sizes be? So these are some unknown, or some questions which impact on performance. And sometimes there's no best answer. What is the best choking algorithm? When do you choke another peer? Well, you want to make sure that you can download as much as possible from them and that they reciprocate, but if they do not upload anything, then you should start choking them. But when is a question to be considered that will impact on performance. How do you make others upload the content? Like one of the questions, how do you maintain that ratio? How do you force others to upload the content to maintain the upload ratio? And coming back to TCP, because we always use TCP for each of the connections, we said when we looked at TCP, it's fair amongst connections. That means if my BitTorrent client has 100 connections across my bottleneck link, and someone else has a web browser which uses just one connection, I will get 100 out of 101 of the bottleneck link, or the bandwidth. That web browser will get 1 out of 101, less than 1% of the bandwidth. That it would be very unfair to the web browser and give a lot of bandwidth to my BitTorrent client. which can severely impact upon other applications, web browsing, voice applications and others. So fairness between BitTorrent and other applications is a major issue. And there are other issues that we don't have time of covering. So that's a quick overview of how BitTorrent allows us to download files from multiple other hosts. Rather than you downloading a file from a single web server, you download from multiple servers or multiple peers. And that's some of the steps that's used. We still have one more topic to go. Any questions on BitTorrent before we move on to that? Don't go looking, don't be surprised by looking for the slides. We've got to go back. We've missed a topic on CORD, distributed hash tables. Any questions on BitTorrent? Are you an expert now? Why not? Yeah? Go for it. Any questions? Oh, you ask on his behalf then. While they're thinking about it. Yeah. Yeah.
Can the like for example be the cost when I try to download a BitTorrent, can the like first be the cost of that when first starting the download, like half an hour the file is start very slow, then halfway through it just speed up.
Okay, first question is about first answer the first question first. Over the duration of downloading a torrent, over that total time, the speed may change. Maybe at the start it's slow at downloading, and then it builds up the speed and is fast, and possibly at the end it may slow down a bit. There are different factors. At the start, remember we need to discover peers at the start. So initially we contact the tracker and find some peers. Those peers may not have a lot of the pieces. That's a first problem. So we may need to discover some other peers over time. So we contact the tracker, get a list of 10 peers. If they don't have all the pieces, then we'll have to find some other peers. Either sometime later contact the tracker, 5 minutes later or so, or contact other trackers which may give us. So that may slow down or mean a slow download speed at the start. So that's one reason why it may be slow at the start. Sometimes it may speed up, and then at the end, as you're getting close to the end, it slows down. Because if you'd use rarest first, at the start, at the end, not to do with rarest first, if you've downloaded many pieces, you no longer have many to upload. That is, you want a specific piece to finish. You need piece 53. You only will accept that piece. So you need to find a specific peer that will exchange that with you. So your past peers that you communicated with may not have that piece. So you need to close the connections or choke them and try another peer that has that piece. But what if the other peers that you try don't have that piece? Then you need to choke them and you need to find a peer that has that piece. And so sometimes at the end it can be slow to finish off. So there are other complexities that the speed may change over the connection. A question?
Why when I set up a lot of connections in one file, the throughput goes to 0?
Why do you?
Like when I have.
You have many connections.
20,000 connections.
Seriously, 20,000? Remember, every connection involves some overhead. With many connections, you need to set up the connection. There's some handshake to set up the connection. So within the BitTorrent exchange protocol, there's some exchange of messages with that peer. You normally, even though you may have connections to many, you do not unchoke them all. The protocol itself unchokes just some of those connections. So you do not use them all. Why does it go to very slow throughput?
Does it involve the NAT table?
That's a different issue. Okay, and the other issue, if you have, your devices may not handle so many connections. Here's your router to your internet. Here's your PC. You set up many connections through the router. Normally a router doesn't have to deal with connections, but you know, I think, at your home internet, you do not get an IP address, a public IP address on your PC. You get a real IP address for your router. That is, your internet service provider gives your router or ADSL modem an IP address. Your home PC gets a private address. And if you have a laptop, that gets another private address. You know, I think from Dr. Comwood's course that this performs network address translation. It maintains some state about who these are and map them to this one public address. And that, depending on your hardware, a network address translation usually can only handle a certain number of connections. 20,000 is probably too many for a cheap device. Buy a more expensive device. Buy a 10,000, 20,000 baht router and it should work. So yes, I think your problem, if BitTorrent creates many connections, this router, which performs network address translation, becomes overloaded. It needs to store information about each connection, and that takes up memory, and it only has a small amount of memory. So yes, that's a problem. Did you work out the question?
Okay, quick question.
Mm-hmm.
You confuse when you downloading BitTorrent and browsing website at the same time. You said that if the download rate is high, but upload rate is very low upload rate, download rate is high, but why he can access website fast? And
But when the upload is high, the web access cannot work. So the question is, okay, BitTorrent running, web browser running. If you're downloading a lot with BitTorrent but not uploading much, web access works. But as you start to upload a lot, web access slows down. That's the question. Why does it happen? So the situation is that you've got two applications on your computer, BitTorrent and web browser, and you have your home modem which connects to some router via internet service provider. And if the situation is, okay, BitTorrent has got many connections and it's uploading a lot, that is, it's sending a lot. So that if the upload rate is high, it's sending a lot. But your web browsing doesn't work. Why is that? Well, the web browsing is very slow. What happens when you're uploading a lot?
Cannot send requests.
Yeah, why can you not send requests? There's a buffer, either at your modem or the router here, but there's some buffer. The BitTorrent is sending a lot, it's filling up this buffer. Whether it's the modem or the router at the ISP, it's one of them, it's filling up the buffer. And then you send a request, and it gets added to the end of that buffer. It needs to wait a long time. It may be even dropped if it has to wait a long time. The request doesn't get out, and the response doesn't get back. So it's to do with whether it happens or not depends upon the size of the buffer and how much you're sending. So basically we get congestion. It's either the ISP's router or in fact even possibly at your modem. If it's at your modem, then you may be able to control it if you can control the size of the buffer or the way that it queues packets. If you can provide quality of service so that if it's at the modem, which packets do you drop? Do you drop the web packet or the BitTorrent packets? Well, drop the BitTorrent packets. That means the upload will slow down, but at least your web will get through. Give priority to the web traffic. So you can do that on some modems, that you give quality of service, apply quality of service control so that the web traffic gets priority in the buffer. It gets sent first. The BitTorrent traffic is sent later. And the response will come back for the web page. So related to congestion, related to quality of service control to fix that problem. Yeah.
I have a very bad idea. I always download at about 8 megabits per second and not upload at all. 10 kilobits per second. And why I still have such good download?
It's because there are so many peers that are willing to download or to send you data. If there are enough peers, then it doesn't matter so much that you download a lot from them but don't upload anything. Because if that peer chokes you, you can move to another one. If that peer chokes you, you can move to another one. If there are a lot of peers, then you should be able to still download. So if there's a lot of seeds, in fact, in that case. So that should be okay.
Do you download a movie from BitTorrent?
Oh, you see my example. I just downloaded Ubuntu. Note that, yes, it's used for downloading copyrighted material, but the protocol itself is quite efficient and is used and some parts of it have been standardized by IETF and other organizations. So companies use it within their networks. Content distribution networks, large companies that mirror websites and so on, use BitTorrent to distribute the content, the mirror images across the internet. So it has its legal uses as well as inappropriate uses. We're out of time. We've got one topic remaining. So tomorrow we need to cover that topic on distributed hash tables. It's reasonably complex. So come awake in the morning and we'll finish that. I haven't written the exam, so I cannot give any hints on the exam. Once I've written it, I'll give some hints. But basically it'll be similar to last year's exam. But let's cover chord and distributed hash tables tomorrow.